All right, welcome back. We are Game 2005 in the fall 2021 semester at George Brown, and we're talking about game physics, week 10, part 1 of our broadcast. So we're going to have a couple parts in this this week that we're going to share. Again, we're sitting at week 10. Last week we did an intro to Unity. I also shared the stuff for projectile motion and energy of a system with those kind of things, with conservation of energy on the slides that I shared with you last week. This week, what we're going to be talking about is 2D collisions and optimizations. So we'll talk about that a little bit for the first part, and then we'll get right into another Unity tutorial, which is for Unity UI and camera controls, which is what we're going to be talking about. So how to move things around with the camera and all that kind of stuff when you're in real time. Okay, so that's what we're talking about this week. Let's get to it because we got a lot to cover and, again, very little time. So I'm going to be talking about fly-through control. So I want to kind of make it so that your camera can, if you wish, fly through the scene. That's the idea behind it. If we can get that done today, that'd be great. Let's talk about collision detection. And again, you've been talking about collision detection with Joss, but he's doing 3D stuff. I'm going to talk about that good old 2D collision detection that we started with when we were doing AI. We started talking about that. And maybe even before that, when you were working with Alex in Game Fundamentals or someone else. So again, we want to make our game believable and somewhat realistic. And again, one of the questions I always ask myself, regardless of what kind of collision detection you're going to do, is what is good enough, right? And to get this right, we need two things: detect collision of two objects that cannot occupy the same space. And after collision, we need response. And we're going to respond through the physical laws that apply. All right, so that's something that we're going to be doing. So there's two types of phases, if you will, or two phases with this. Broad phase, we want to check collisions with every object on the screen that could be computationally expensive, right? And so sometimes what we can do is we can use a static grid or some kind of spatial hash to divide the space. Like right now, what you're doing with Joss is you're doing collision detection. The more objects that are on the screen, you're doing a shape collision detection for every object and every other object. That's what you should be doing, right? Which means you'll have a collection of structures, as an example, where you're going to collide, almost like a list of structures that you can use to kind of say, okay, I want to check my collision detection between this list and this other list of different kinds of collision shapes, right? And that can be really computationally expensive. So what you can do is you can break this down into something called a static grid, whether it's 2D or 3D, and you divide the space down. And what you're going to do is, as the shapes get, if the shapes are close to each other, that's when you're starting to do your collision detection. So again, if you were to draw this idea out, right, and if we had imagine if you have a screen, and whether it's 2D or 3D, here's your screen, and you have an object down here, and you have another object over here. So all these objects are kind of far away from each other. But what I'm going to do is I'm going to really, I'm going to check, does this object collide with this one? 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 This one, right? You're going to make all these objects. And the more objects I add, the more collision checks we're going to make, right? And that's not efficient at all, right? As an example. So instead of doing that, what the spatial hash does is it kind of, there's different ways of doing this we'll talk about in this lecture, right? But we want to think about how can we divide or subdivide our world or game world so that, there is some kind of division scheme. Okay, so I'm just going to divide it in, kind of a broad grid, right? So here's a broad grid. And again, you don't have to make it so that it's even an equal, a grade in equal amounts. Think about these divisions, right? Each of these objects are sitting in different, locations, if you will, right? And they're in a different dimension altogether, right, than each other one. So we really don't need to do collision detection because this one is even close to this one, or this one, or this one. And if we were to move, let's suppose, again, I want to move this object, and I want to move it here into this area, right? So if it was originally here and now it's coming into this area, we can further break down the grid. So we can hash this grid again and say, okay, so this object is moved, right? Let's, break the grid down even smaller, right? As an example. And this hashed space is kind of something like where we say, well, you know what, we're getting closer, right? But again, these ones are far away, but these ones are still not close enough to do a collision check. What we want is if it's right in here, right, as an example. So again, we can continue to move the object, right, inside the space. We can say, well, once the object gets here, then we start doing collision detection. It's close enough that we're good, right? And we don't want to check distances. Distances, remember, is a bad thing to check, right? Neil's asking, should we do this for assignment 3? Not necessarily. In assignment 3, you're working with three-dimensional grids. But the idea here is if you wanted to, you totally could do an optimization like this, where, you know what, these objects, they have a chance to collide. These objects here don't have a chance to collide. They're in kind of different quadrants, if you will. I didn't really draw the quadrants really nicely, but the idea here is that you want to keep on hashing or subdividing the grid further and further until you know that they're close enough. Objects are close enough where I'm probably going to have a collision soon, right? This is where you start checking. Now, there's advantages and disadvantages to this approach. One of the advantages for this one is that, we're going to get, this is the narrow phase stuff that we're talking about. So we go from broad phase, is there anything near, to narrow phase. Okay, now things are closer and there's a chance that they're going to collide, right? And what we want to try and do is we want to look at, collision shapes like a sphere. Sphere is like the basic collision shape. It's the easiest one to use because it has really only one thing to worry about, radius, right? You have a center point and a radius, and if the radius is, if the radii overlap, right, then there's most likely a collision. That's kind of the easiest way to do it, right? So that's what we're going to be starting to talk about. But so we can surround an object with a sphere, right? And it really comes down to whether the outer surface of one object comes in contact with the other outer surface of another object. And for complicated asymmetrical type objects, this analysis can be quite difficult, but it simplifies considerably for basic geometric shapes. So if I use another sphere is pretty easy. But if I'm surrounding something like a bunny like this, because there's blank spaces in the the sphere boundary, right? So we have, some blank spaces here and here and here and here. Let's suppose these two spheres are colliding, but they have an asymmetrical shape inside. We're going to see a logical collision when these two things overlap, but we're not going to see a visual collision. And the visual collision is going to take away from our immersion in the game. It's going to, it's not going to look right. And we want to try and avoid them. And so we can have, we can add other collision shapes instead of just a simple sphere to accomplish this. So again, when it comes to sphere, sphere, or circle, circle, we only care about the distance between radii. So when you have the distance between radii or centers, you take the distance between centers, and if you add up the radii together, so let's say radius 1 and radius 2, when you add them up, and if they are smaller, right, if the distance is shorter than the combined radii, right, so if radius 1 plus radius 2, if the distance is less than those, then you have a collision. And again, what we can do is we can use squared distance, and we can multiply this squared radius like we've done in the past. And one of the questions at the beginning is, can we use vector 3 distance for the assignment? Yeah, it's just a distance calculator. I don't think it's going to be negative. Why would I ask you to redo the formula on your own? However, you're going to notice that vector 3 distance, Neil, is not efficient. It's computationally expensive because in the back end it uses square root, which we don't want, right? So squared distance, you may want to make your own, which is squared distance, which might be better than just a distance calculator. So here's an example of just circles. Again, you can expand this for 3D, no problem. You have two circles. Each circle is an object, and this is just pseudocode, right? As an example, is an object that has a radius as well as X and Y coordinates. That's really what a circle is at the end of the day. If you expand it to X, Y, and Z, now it's a sphere. Okay, so X, Y, and Z coordinates for your radius, for your object, right? And you're going to use math.square root or some kind of, in Unity, mathf.square root. At the end of the day, when you do this, right, if you use a square root, this is bad because what you're doing is you're calculating the distance. This is exactly what we're saying. If the distance is less than the circle 1 radius plus circle 2 radius, we have a collision. And we've seen this, collision detection in our previous games, right? So again, we can also think about whether a sphere has collided with a horizontal or vertical surface. And this is what we've been working on with Joss, different collision shapes. If the distance from the center of the circle to the surface is less than or equal to the radius of the sphere, right, then a collision has occurred. Okay. So again, that is pretty easy to calculate, right? So plane and circle, or plane and sphere, or line and circle. It doesn't really matter how you look at it, right? Another basic geometric shape is the cylinder. So again, you've got two circles, right? And you have a line segment that goes from one of the centers to the other one. So the distance of this line segment is almost like, think about a swept circle that kind of, is many infinite amount of circles to kind of connect to the top circle from the bottom circle, right? That's how many circles it is. You just fill in that distance. And to emulate this, we can have in 3 dimensions a circle at the bottom, circle at the top, and a line segment that kind of goes between them. And the line segment says how many of this, what's the space that I'm going to overlap with. So it's pretty simple to think about this, right? So there's some different methods of creating a collision sphere around an object. Again, what we can do is the center of the sphere is equal to the object's, or all the object's origin point. So let's say the common point. So we put that's the center of the sphere. And then we would loop through all the vertices, right, and subtract each from the center, finding the highest magnitude. So what is, like, if I had the vertices of an object, let's say a 3-dimensional object, then I'm going to loop through each one of the vertices and say which one is the farthest away from the center. That is going to be my radius, whatever the farthest point is from my circle center, or my sphere center. And then we're going to average all the the vertices. We can find the center point of that object. We can recenter the center point, right? And we create an axis-aligned bounding box, if we really want to, around the game object and fit that inside the sphere. So this is kind of an interesting way of doing things. And there's a chance for the objects to be inside each other before a collision is actually detected. And this is very common. And normally once a collision is detected, you have to reposition the object correctly. And this is usually unnoticeable in games. And the reason why we reposition is because, again, if I was going to go back to our example that we're drawing, so we're colliding every frame, right? So we're starting to think about, collision detection, and we're saying, okay, so here's an object, right? And let's just use circles here for our example, because our example is about circles. So I have this object as an example, and I have another similar object, right? So here's another object. And what I want to do with the second one, right, is for this object here, it's moving, right? So I'm checking collisions every frame. Let's say we're close enough. We've done broad phase, and we're now in narrow phase collision detection. And as it comes closer, imagine we're moving a certain distance every frame, and in the next frame we move to this distance, right? So it's already occurred, right, between frames. The collision detection's happened already, right? So to visualize this, it may be cleaner, right? We can think about frames as different time steps, right? So imagine, if I'm just going to draw it roughly, imagine there's a frame here and there's a frame here. This is the, the frames, right? This is when frames occur, right? And I'm just going to make it roughly around right. So again, if I move a certain distance every frame, right? So let's try this again. And let's say I start way over here, right? And then the distance I move in one frame is this. And the next distance I move in one frame is this. And the next distance I move in the next frame is this. We have an overlap, right? And the thing is, it can be wildly overlapping if the object is moving fast. So what we need to do is reposition. So wherever the point of entry was, we need to reposition it to that point. Okay, that's what we're talking about. And that can happen easily because of how fast an object is moving every frame. Okay, so faster moving objects that are slower have another problem, right? Like we talked about before. And we're going to talk about this. Let's suppose, this object here, right, is actually, let's just do this again. Let's suppose this object is actually smaller, right? So we're going to make it smaller. So it's much smaller, like a bullet, right? And we've talked about this before, right? We said if an object is small like a bullet, it's going to be hard to see this one, but let's suppose that's true. So now we can move the same distance. Let's say we're moving, but we're really moving fast, right? And we're moving really fast. We can almost move from one frame to the next. And as we accelerate our bullet, we can move clean through without a collision detection because we were here and then the next frame we're through, right? We're not even colliding anymore, right? This idea that we're talking about for a small, fast-moving object is called the tunneling effect that we're going to be covering in this lecture. So how do you deal with this issue? Because it can be happening with you too. By the way, this effect is not just for 2D games, but also for 3D games. If I have a fast, small object, then it can barrel through or basically tunnel through any surface before I have a chance to detect it. Okay. So that is the repositioning thing. I want to be able to reposition an object so that it is something that I can see, right? So again, collision spheres are often used as a preliminary check to more expensive algorithms. Sometimes what we do is we put a collision sphere on the outside, right? We know we're going to collide. And then on the inside, we have a more, kind of detailed collision detection algorithm. Maybe we have another algorithm inside the sphere algorithm, like double collision, right? So again, when we on the technical side, the process to compare collision spheres is very efficient and fast. The downside is that it's not very robust because it can happen very quickly. We talked about the tunneling effect that we talked about before. Another basic shape we've seen before, there's two. There's an axis-aligned bounding box. You learned about that like year one in game fundamentals, axis-aligned bounding box. And there's another one called the object-aligned bounding box. So axis-aligned bounding box works on the same axis, but object-aligned bounding box, once we go there, we start thinking about how we can work towards, aligning an object in according to every other object. So an object-aligned bounding box, okay? All right, let's take a look at that a little bit. So axis-aligned bounding box we've seen before, right? It's they're called AABBs as a short form. It's easy, and the reason why is we want to talk about the overlap from the extents. The top left corner, bottom left corner, bottom right corner are the two pieces of information we really need. Anything between the top left corner and the bottom right corner, you have an overlap. If you have an overlap, you have a collision. The fancy reason why axis-aligned bounding boxes are easy to calculate is because they're all on the same, they're using the same axes, X and Y coordinates, the X and Y axis or the Z axis, right? The challenge with these things is that they don't give us a very good approximation when it comes to how true objects work in a physical world. But we'll talk about that in a bit. So again, axis aligned means that they're aligned with the world. The box is then in world space. That's what we have to think about, right? And here is a very simple piece of code that we've seen similarly before, right? Where we have two rectangles, right? This is in 2D again, where you have X and Y coordinates for the top left corner. This is where it starts. Then we have the width and the height. So 50-50 as an example. And another box that is in at 2010, that's where it starts, the top left corner. And then the width and the height. So we kind of match out the bottom right corner, top left corner, bottom right corner. Once we have these numbers, right, then we can start thinking about is a series of checks, right, of branches. If my rectangle.x, rectangle1.x, is less than rectangle2.x, right, plus rectangle2.width. If it's less than, these all of these checks have to be true in order for a collision to detect. So think about what this is saying. If the value, right, so 5, is it less than, rectangle 2's 20 plus the width, which is 10, 30? Is 5 less than 30? The answer is yes, right? Because this would be 30. And we can write this down together as an annotation to check this case. So the first one is 5 less than 30? That's what we're saying, right? Because 5 is the x-axis, the x number. Rect2.x is 20, and then rect2.width is 10, so 30. So it's 5 less than 30. The answer is yes. Okay, how about this one? Is rect1.x plus rect1.width, x 5 and width is 50, so that's 55. Is 55 greater than rect2.x? Is 55 greater than 20, right? And then the answer to that is also true, right? And we'll talk about why these in a second, right? But we'll just map this out so we can see if there's a detection, a collision detection that we can see, right? So again, rect1.y, now we're going on the y side, is 5. Is that less than rect2.y, which is 10, plus rect2.height, which is 10. So 10 and 10 is 20. So it's 5, like we said, less than 20, right? The answer is yes, that's true. So again, we can say that this is true, right? This is true. So far, we've checked every single one, every single box, if you will. And the last one is rect1.height plus rect1.y. Rect1.height is 50, and rect1.y is 5. So 55 is 55, right? Is that greater than rect2.y? Rect2.y being y, being 10. So that's 10, which is also true because each of these checks is true, and that's how it would evaluate. Then we can say that a collision has been detected. Now, and this is kind of what we're saying down here. So why is that? Why is that, right? Because what we're trying to do is we're trying to think about, we're trying to think about objects in space, right? 5, 5 is the top left corner of the screen. So if I was going to draw this out for you, and we had a little screen to draw out, so let's do that. And I'll approximate it as much as possible. Let's suppose our screen looks like this, right? Here we are. And we say 5, 5. Let's see if we can draw this. So 5, let's say this screen is in the middle, and this is about, I don't know, we'll say 500. So if this is 500, this is 250, this is 125, this is in the middle of that, and so on. 5, 5 is probably like right here, right? Like right in the corner. So 5, 5, and then 50, something like this, and then a height of 50. It's a square box that we're talking about. So that's the square box, 50 by 50, 5, 5. The other one is at 20, right? So it starts over here somewhere, right? So, we can say 5, 10, 15, 20, something like that at 20, and y is 10. Okay, immediately we see that we start inside the other box, right? And then it goes with a width of 10, right? And a height of 10. That's what we're talking about, guys, right? So this is number 2. So this is box 1, and this is box 2. What we're saying is this corner here, right? And when we compare one object to the other, right, we're saying, hey, take the two objects, whatever they are, object 1 and object 2, and here are the extents, the top left corner and the bottom right corner, the top left corner and the bottom right corner, and that's what we're checking. Okay? So, cool. So what about 3D axis line bounding box? We can use rectangular prisms as AABBs, right? So they're not quite boxes, they're rectangular prisms. And the collision test is the same, but with the third dimension added in. AABBs are mostly used in 2D games. Why? A majority of 2D games use sprites or bitmaps, right, as an example. So they're very easy to do. Normally, sprites are exported or created with minimal space on the sides and the top and the bottom, which is where the majority of collisions occur in 2D games, right? Sometimes we want to use other collision shapes even in 2D games, like I've talked about before, because you have that weird, logical collision, but there's no visual collision, right? So one of the things that we also can talk about, and I think Joss is also going to talk about it with you, is something called separating axis theorem. So AABB is an approximation, right? It captures most of it, but sometimes what happens is we want to be way more accurate, right? Way more accurate. And especially when it comes to 3D games, right? We want to be more accurate. And what if for example, I don't have a box that's axis aligned? The box has been rotated somehow, as an example. If the box is rotated, then what I want to do is be able to detect the collision between any if I can draw a line or a plane between two objects from any one side, right? Whether it's this way, or this way, then obviously if I can draw any line between them and that when they're not touching, right? Then chances are the idea is that there's no collision, right? Here, I can't draw a line on every axis. I can't do it. There's going to be some place I can't do this, or this. You can see that if I draw the same line here, it doesn't matter how it is, they're overlapping because my line, there's no clean axis that I can capture where I can draw my line cleanly through these things. So therefore, there's a collision. That's how we kind of figure it out. And this works great. It's way more complex, SAT, so separating axis theorem, but it's much more accurate. It is more computationally expensive, but not a great deal. And what this does is it makes it so that your objects are much more accurately, kind of described in terms of collision detection. So, again, it's a technique for calculating collisions between convex polygons, right? Convex polygons, remember, there's a difference between in geometry. Let's talk language a little bit. And when we talk about lines and polygons, let's draw some convex polygons. And if I was going to do that, let's just use lines to do this. Actually, we can probably use this one. So if I'm going to draw a convex polygon, it's where the objects are, now here's concave, but let's just draw, here, let's undo that change. Let's try that again. I was going to draw a concave one, right? Convex polygon. There we go. That's a convex polygon, right? So roughly, right? Because all the edges are outside of each other. Concave polygon is where if I draw it again, imagine if I draw a shape like this, right? That is a concave polygon, right? That's not a convex polygon. Why? Because of this, right? We have an object like this. So concave polygon, convex polygons, nice and easy. Concave polygon, SAT, we're going to have to break this out a little bit different. Why? Because we look at all these vertices. So we start looking at, this vertex. We look at this vertex, each of the vertices, and we try and find, we use an algorithm where we look at all the verts inside the polygon, right? And we say, hey, can we kind of create a shadow, from one vertex to the next? So if they're far apart like this, that is okay. But what about if they're close together? So let's suppose that these are closer together, right? So they're overlapping like this. How do I detect that weird overlap, right? How do I do that? Well, what we typically do is we have we can use axes again in a two-dimensional space, right? So imagine that this is the, like we normally have, this is the y-axis up here, right? Here's the y-axis. And we know where the x-axis is, but let's map it anyway, right? So here's the x-axis. And you want to see if these polygons are colliding. So what you can do is you can do something like projection. It's called projection. And what you do is you take each of the points on the polygon, right? And you project it to both axes. Okay, so let's try that out. Let's go into this and let's do that. So I want to say this would project onto this axis. Think about like shadows, right? And you can see that, you know, these points project here and this projects down there, right? And simply put, when we look at this axis alone, you can see that these lines here are overlapping with these lines down here, which means on the y-axis, we have a collision, all right? And the same thing goes this way. We can kind of project down this way. So we can say, let's do this. And we can take each of the points on the polygon. And again, complex polygons like this is what you would do. So you kind of project all these points down and say, well, look, if the extents, right? And I'm just going to make a different color here so we can see the extents. So let's look at the weird polygon. We'll make the weird polygon blue, right? So a blue color, right? And let's suppose the extents of the weird polygon, so this one, right? And this one. So you can visualize it. Here are the extents of the weird polygon, right? As they interface or they're projected onto the axes. And this is only in 2 dimensions. Can you imagine when you're in 3 dimensions? These are all the calculations that you can make, right? So these are the extents. And what about, let's make the extents of the other one a different color. Let's make it like an orange color, you know, so we can see something different. So these are the extents of the normal looking, you know, convex polygon, right? So this is the extents, right? We don't have very many and a lot less vertices to deal with, but this is the extent. So we can say that, hey, look, we know that this piece right here, right? So we know that if this is the regular polygon, right, we care about this piece and this part, right? This part here is the shape that is created, or if you look at, let's undo those 2 things. We really care about this piece right here, this part right here, and this piece right here. We care about those things. Do I have some part of the other polygon, the weird polygon, inside of that's projected within this this space? And the answer is you do. You have this part and you have this part. You have another overlapping shape, 2 overlapping shapes that are kind of here. So you can say we clearly have a collision across the y-axis, and we clearly have a collision across the x-axis, right? We have it on both, right? And if you look at it, the other problem is we also have to check on the z-axis, because on the z-axis, even though it's colliding on the x-axis and the y-axis, it has to be colliding on the z-axis as well, because we're seeing this from the side view, right? But if we take this weird polygonal shape, right, as an example, and we project it deeper into the z-axis, it might be like over here, right? Actually, farther away, like way farther down in there, right? So even though it appears close to us over here, it's actually not like that. It's off a little bit in the 3rd dimension. And so we need to collide like this on every axis. That is a way of calculating very, very cleanly by using vertices. But can you imagine when we want to find the extents of an object, we need to find the, you know, all of the vertices of the object, map them into some kind of list. And after we take that, we want to find the vertices that are the farthest on the x-axis, the lowest on the x-axis, the minimum and the maximums for the x-axis, the y-axis, and the z-axis. And once we've done that, we find all those verts. We want to create an algorithm to say that, okay, now I have extents. I want to compare that this line segment intersects with this line segment intersects with this line segment, and this line segment intersects with this line segment in a 3-dimensional space. And when I say line segments, what I mean is we can create line segments that go from, let's use the orange line again. If I want to make a line segment that I care about the line segment, Tom, I care about the line segment that goes from here to here, right? And I'm kind of creating a line segment that I want to interface with. So does this line segment interface with, let's go and do that blue color again. Again, I'm picking a close blue, probably gonna be not the same, guys, sorry, right? Does this line segment interface with this one? is there an overlap? And we cleanly can see that, right? And the same thing goes with this line segment here, which is the blue line segment that's created by the projection of the extents, the minimum and maximum points on the polygon as they're projected down onto the x-axis. When we say projected, it's almost like you draw a line between these points and the x-axis and these points and the y-axis, right? If we have an overlap and they have to overlap both places, then we have a collision in 2D. If it's 3D, all three axes have to have a collision. Okay. Neil says, it seems difficult to make this efficient. Well, the way to do this, if I was going to do this mapping out with you, would be to, let's get a list of all the verts, right, of an object, every single vert, right? Because we need to do that, right? Especially for complex objects. And once I get the vertices of all the objects, and then we're talking about polygons now, not spheres. Spheres, that's a different thing altogether, right? We wouldn't use this kind of algorithm for spheres. We would do sphere collision detection, right? But we want to get the extents, right? The extents of the object. And you can even calculate the extents of a sphere by basically saying, hey, what is my center? And what are my radii in 3 dimensions? You know, kind of stuff, right? So, or look at the radii, you know, from the middle of the center of the object, you know, towards the top, almost like the diameter. I can kind of create a box around the sphere and say, what are my extents when it comes to the radii, right? So how far does that object go? And then does it overlap in with another object like this? So again, if I was going to do it with a sphere, let's do this kind of thing with a circle, right? And let's add a circle in there. Let's add a circle over here, right? How would I do it? Let's make another color for that. So we'll say green, right? So if we were to try and do that overlap, and let's say here's the circle, right? We clearly see on this side, at least from the X and Y axis, that it's not colliding. But this circle could actually be, you know, colliding on the other axis, or, well, chances are it's not if it's like this, because it's not colliding on any of these two things. It's not colliding. Because I can clearly draw a line between these two objects. Remember, separating axis theorem. I can draw a line on one axis, right? Then that means that there's no collision, chances are. But let's see how I would do that. So I would do the extents, right? So I would kind of draw a line, let's say from, here's the center, right? And I would draw a line down into the middle, right? So here's I would reflect down this way. And the same thing goes with this, right? So on the y-axis, it looks like we have some kind of line that's projected. I would also project a line from the extents. So here's the line that almost like a shadow, if you think about it. That's what we're trying to do. We're kind of creating a shadow that kind of projects the circle onto the axis. Same thing for here, right? I project a shadow down this way, right? And I'm just approximating, guys. Use my eye, so forgive me, please. But here's a shadow that I'm doing down here. So you can clearly see that the line segment that's created here, right, does not intersect with any other line segment. So therefore, there's no collision. But you can do it with the sphere as well. All right, so sphere versus weird polygon, right? And that's why SAT works good. You can work with any shape that you want, right? It doesn't matter whether it's a rectangular prism or something else. It's okay. All right, when it comes to do I collide, right? That question. So going back to this, again, we take these shapes and we create projections on the axes. Once I create a projection on the axis, if we have any separation like this at all, then there's no collision. There's no collision, right? So it says the shadows of the objects must be touching. If you find a gap, they're clearly not touching. And if you have one that's clearly not touching, then it's going to be there's no collision. So that's the way to do it. And it talks about some algorithms and how this works. Now, so how do you code SAT to work in 2 dimensions? So first we kind of take a side that we're testing, right? As an example, we're testing this side, right? Instead of reflection or projection, we take this side first. We try and draw almost like perpendicular to this this plane itself, a line between this plane and this object. Okay, that's what we're doing. and we project it down onto because this is like an object-aligned bounding box. We don't care about axes, if you will, right? We project it down to here, right? Almost like we've taken this object itself and we project it down to the other extents, right? Once we have this, right, then the next phase is to do the same thing with the other object, and now we have two line segments, right, like we said. And once we've got those two line segments, we can clearly see that they don't touch, right? So because they don't touch, there's no collision, right? That's what it's basically saying. It's pretty cool. It's pretty good. Pros, fairly fast. Uses pretty basic vector math, and you can bail out of a test as soon as a gap is detected, which eliminates unnecessary calculations, or because you're doing branching, right? So you want to kind of every check. You're doing multiple checks, which means that any one of the checks that fail, you bail out of the test, so it's much quicker. I mean, worst case scenario, you'd have to do a check for every single one of the vertices on a complex object, right? Now, what it says is it only works well with convex polygons. Complex shapes are out unless you build them out of smaller convex shapes, because if you go with convex, like that weird shape I made, right, the problem with that is in some scenarios, if I was to rotate that shape, and especially in 3D, it would look like they're not colliding, but they are. That's why it's not, because we're using kind of like the shadow effect that we're doing. We're projecting, and the projections would look like or sometimes we'll get false collisions. It looks like we're colliding, but we're not, because of that weird convex shape. That's where it becomes weird, all right? It doesn't tell you which sides are touching. It doesn't tell me how I collided or where I collided. It only how far they are overlapping and the shortest distance to separate them. That's all we know. So there's some disadvantages to using this system as well. Pros and cons. So again, we did exactly that. We have these dots, right? Each dot would be a vertex, box 1 and box 2. And we take all the dots into play. Again, first of all, we need to prepare the vectors, and that's what the first step is. And I've kind of put the pseudocode in here. And then once we've prepared the vectors, we want to use a min-max projection on box 1. And you can see a similar approach used on box 2. All right, so that's what we do. Box 1 and box 2, we do a dot product. Josh should be talking about that with you guys. You know, how we project stuff. We use dot product on a particular axis, whatever that axis is, right? And then once we've got that, finally, we evaluate whether there's a collision on that specific axis. And we need to do that for every axis. If there's a gap on any axis, there's no collision. That's the most important piece. So that is separating axis there. Questions around this and basic shapes. Remember, we can always combine shapes. That is the other way to do it, but it means double the amount of calculations. So some people have a way of getting around this idea, and they say, wait. Why even bother with any of this stuff when I can cut it down even simpler? I use axis-aligned bounding boxes, planes, and spheres, and I'm good enough. I don't need separating axis theorem. Maybe. But let's define a different polygon again. So let's just choose a different color to do that. So let's suppose they're both polygons that are convex, not concave. So they're kind of like this. They start off like this, and you know, yeah, we'll do one of those. There we go. That's convex. I was going to make concave again. And let's make another one, right? And we'll make it some separated, and we'll put it together. Okay, so again, we'll make kind of a weird diamond shape, right? So an object that's kind of long and like this. This is not going to comply to a AABB, right? It doesn't work well, because if I was going to try and take an AABB to surround this thing, remember what we do is we use a box that kind of puts this in play like this, right? We put a box around this. That's what ABB would work like. And we put a box around, let's try that again. We put a box around, sorry, gotta use my eye for this one again. And my eyes are not like your eyes, guys. But you can see, forgive me, we put a box like this, right? Approximately, right? So you can see that there's gaps. There's, you know, the gaps we talked about before. We have this issue here, an issue over here, an issue over here. this part, there's a lot of areas where, if I was in a 3D space, that this might cause a logical collision without a visual collision. So it would be a problem, right? And we don't want this. So this is not optimal, right? And we can also try circles or spheres, collision detection. But the problem with that is that you're going to have, in some cases, even more of a gap. If I tried a sphere here, you're going to have like a gap way over here and way over here because of how this looks. Here, a sphere might work, right? Because it's kind of, you can probably fit a circle around this thing pretty good. Like if I was to do let's try that again. If I was to do a circle, let's say from the center, right, we can probably fit most of the verts with some adjustments, adjusting the circle. I can move most of those verts in something smaller than this, right? But the problem with this one is if I was to try a circle from here, yeah, well, now we're in trouble because we can't do a circle like this. That only encompasses 2 of the verts. What about these ones? So now we have these areas here that we have big gaps. So that doesn't make any sense either. So those things are bad. Circles are bad in this particular case, right? So what you can do is people chop it down. They kind of make it so that they have multiple, boxes. So they create a box, and let's undo those shapes. They create a box and they say, okay, well, we have this extent and this extent. Let's create a box. So they do this. They kind of sit there and go, okay, we'll make a box here, right? And again, we'll continue the box. So we'll kind of make a box here. And we're like, well, that doesn't really work because we have this one and this one. Okay, cool. So let's make a box between this one here and this one. So there's the next box. See what I'm doing? And you can definitely calculate this. It's not impossible for you to do, right? Because what you're doing is you're just taking 2 of the edges and creating a box for each of the edges. But now, what are we getting? Remember, each box is an axis line bounding box. Each box, guys, which works out to be, as an example, 1, 2, 3, 4, 5 boxes, 1 for every side. That's 5 times the calculations that you would normally make, right? And it's not going to buy you, there's still going to be some spaces, especially for these ones. This one, this one, this one. This one's not so bad because it's kind of, the angle's not so steep. And maybe I made this one really big, right? So we could probably make a box that's a little bit smaller. So we kind of, from the extents, we can kind of go to there. That might be the box instead of this one. But the idea is you still have this area, and all of this area. It's better, but it still maps out the box the same way, right? So then you can go into smaller boxes or smaller spheres, right? So I make a sphere here, a sphere here, a sphere here, and it becomes like you're cutting the object up into different pieces. So that is, and again, there's algorithms that you can figure out that might make this better. But think about this one. I mean, you're not going to get much of a savings if you did that, right? So imagine if I made a box here and I made a box like this here. Doesn't matter. Project this in 3 dimensions, guys, right? Look what you're going to get. You're going to get pretty much what I would get normally. Let me undo that. If I was going to just draw one big box, right? Here's a trick though. In 3 dimensions, depending on your camera, you may not notice. 2 dimensions, you'll notice. 3 dimensions, you probably won't, right? And you won't because the collision detection is going to be so fast, right, that you're going to be pretty accurate in terms of it's going to look good, right? It's going to fool you for the most part. It's where we get smaller objects that are closer to the camera that you're going to not get fooled, all right? So that's kind of stuff. That's another option that you can make, some box. What about this area in the middle? Well, we don't care because you've already gone through this one, this one, this one. You don't care about the middle one. Although you can make a box there as well. So these are different techniques you can use, right? Or you can slice this up even thinner with smaller boxes, just like we would if we were going to do a curve on to do an integration. Smaller boxes, smaller rectangles are going to be able to map out this area a lot more, right, from the center. So that's another option you can do. So you can, instead of mapping it from here, what you can say is, okay, I want to kind of map it from the center every single time. So I take the center of the object and I kind of make a very thin slice and say, okay, that's pretty good, right? And then do another one, another thin slice for this one. And we don't want to go beyond kind of the extent. So you kind of do something like this and you keep doing that, slicing, 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 slicing. That doesn't make any sense to me, guys. I'm sorry, right? So but you could do that across the entire object if you really want to. And people have tried all these different optimizations before, but the one that works the best to me with convex objects is that separating axis theorem. All right, so we've talked about this at length. Any questions around this? Is just a revision or a review of 2D collision detection at this point. Any questions around this? Because that's what we're covering here. Again, I've showed you a couple of formula, and it really applies to 2D, okay? Next week, we'll be talking about 2D collision response, and then we're going to get into 3D collisions and 3D collision response the following week. And Joss will be covering some of this as we go. So I want to stop recording now and get into, put it on Discord. Sorry, I got a question that's coming through on Discord. One sec. Let's see if I can see what that question is. Yes, yeah, it is a false positive, Nick. Nick added an image on Discord that looks kind of like this, and we can see that that would be a problem, wouldn't it? Right, because we have, this looks like we're colliding because we have a very thin shape, and here we're not colliding, but here it looks clearly like we are because we have a very, very thin object here that is appearing. So this is where we have some false positives. Yeah, absolutely, right? All right, and that's why you would use, instead of using the axis, what you can do is you can use I'm using the world axis when I did my example, but you would use the object's axis, each side of the object. So going back to that before we stop talking about this and move on to the unity side, the unity hour, which is what we're going to be doing. Let's suppose we use SAT the way it's supposed to be used. We kind of work down this side. So we sit there and say, okay, well, we're going to make kind of use of the projection. We're going to project down this side. We're checking this side first. So this is the side we're going to project down, right? As an example, we project down to here, and we'll project this one down to here, as an example. And then we have this length that's down here, and we can draw a line. If I can draw a line that goes from here to here, right? And we use this one when it comes to the object aligned axis, not the world aligned axis. That's how SAT works. It kind of starts projecting along these points first, right? And if you look at that previous diagram, right, which is this is how it works. It kind of creates an axis here, and then we start checking along this guy's axis, right? If there's a gap, that means there's no projection. So again, think about this, right? I've projected down here, and I'm going to do the same thing with this. I'm going to kind of make this line that kind of goes all the way this way, right? So let's use this axis. The first thing we're going to check, right? So this is the axis that I'm checking, right? So this big line. And then, forgive me for this thing. And then, you kind of take the closest things and start projecting down that way. So we take this one, this line here, this whole side, and we project it down onto this line, right? And this side, and we project it down to this line. And we clearly have a gap, so there's no collision, right? And if we were to do that again, let's suppose we bring this closer. So we do have an overlap, right? And these are good questions, but let's suppose we did that. So we bring this object so that it's like this, right? So now clearly we have an overlap, and let's see how that would work again. So let's check the same side. So if we check the same side out and we project, so we take the axis, we want to check this side first. It doesn't matter which side you check first, by the way, and we're going to draw a line that goes here, and we draw this line that goes here, and we draw a line between the two things. So we kind of say, let's draw a line that goes between those 2 points, right? Something that looks like this, right? Then we have a point here and a point there, and then we do the same thing for this this side. So we kind of project, the points, right? And we can clearly see that when we do that, right? When we start projecting, because there's no place to project to, right? That we have a connection here and here. There's an overlap between this one, and therefore we have an overlap. That's how it works. right? But using Nick's example, right, then if you did it the other way around with world-aligned axis, world-aligned calculations, the problem with that is you're going to get that shape, that weird possibility of false positive. Okay, so again, you might think this is challenging, but again, there's formula out there. SAT exists. You can write your own SAT code, no problem. And the great thing about this is going to give you more accurate responses for convex objects. Concave objects, that, because you're going to have something similar to what Nick showed us online. All right, so that is the physics hour. Let's get back into the Unity hour. And the way we're going to do that is we're going to shift gears a little bit. I'm going to stop, stop streaming on YouTube right now, and then start a new stream just about Unity. Yeah.